Alrighty, our last lesson, everybody. Brings a tear to my eye. Bolt, your lessons always make me cry. I don't know. Always. Let's do this, ladies and gentlemen. If you watch the video for homework, this shouldn't be too bad, okay? This shouldn't be too bad. It's a pretty easy extension from that. The background is all the same. We are going to be doing a t-test for a slope, for a regression line, okay? So let's do this. I took the same scenarios as the video from the homework, so hopefully that makes things more familiar to you. So how much is a truck worth? So this is the scenario where we have a truck, we're selling it, and hopefully it makes sense that the price that you can get for the truck kind of depends on how many miles it's been driven. There's an association, there's a relationship there. And so for homework, you made a 90% confidence interval for what that slope could be, okay? But another way to look at that question is not what the slope could be, but is there actually a slope? That's this question. Is there convincing evidence of a negative linear relationship, okay, at the alpha 0.01 level between miles driven and the price of this Ford F-150, all right? So it does make sense that the more miles you drive the car, the less it's worth, but do we actually have evidence of that from the numbers? A little scary for me. My car has 174,000 miles on it. Yeah, that makes the value go down quite a bit, but does it? So let's take a look at our data. Does it support that? We will do our 4-step procedure as always. So our null hypothesis here, we're going to test this, is that the population slope is equal to 0. That means no association. The alternative is what we think it might be, is that there is a negative linear relationship, that the slope is less than 0. Then, of course, we always have to add context where is the true slope of the regression line. I might say population regression line. Relating context. The true slope of the population regression line relating the price of a Ford F-150 and the miles it has been driven. Now, you might be thinking, Bolt, what the heck is that weird curly B thing you just drew right there? What is that? That's simply a Greek letter B, okay? That's simply a Greek letter B. So if you remember, real quick little background for you, our regression equation is y equals a plus bx, where a is the y-intercept and b is the slope, right? But that is all from our sample, which is why it has English characters. If we're talking about the population, the parameters, that's when we use Greek, right? So for the slope, that's the one we're interested in. The slope, that's where we use the Greek letter B, that is beta. Okay? That's why it's the capital Greek B right there in our hypotheses. All right, then the next question you might, I hope, have is, where the heck did 0 come from? Why is it b equals 0 and b is less than 0? So the b equals 0 means there is no association. No association. Or no relationship. So if there was no relationship between miles and price, then our scatter plot would just look scattered. All right, there's no upward or downward correlation here. If there's no association, it is simply a scattering of points. And so if you were to do a linear regression on that, well, it would just be a horizontal line. There would be no slope, right? So the slope would be equal to 0. So that's why the null is 0 in this case. If there's no relationship, then the slope is 0. But if there is a relationship, then we will have a slope. And if it's a negative relationship, then it will be less than 0. Okay? So that is your null and alternative hypotheses. Plan, I'm not going to do it. You're going to read about this. Okay? But again, I'm pretty sure that's always going to say, hey, the conditions for inference have been met. All right? Every problem I've seen has that in this context. So, but you're going to read about those just so you're familiar with them a little bit. It helps me sleep at night, all right? I don't like skipping things. It feels weird. But moving on, because that would probably take like an hour of Bolt talking, and nobody needs sleep that badly. So, the do. Let's do the do. We are doing a t-test for slope. We are doing a t-test for slope. Let's see. It's been a while since we've written a regression equation, so let's do that. So remember, our regression equation is y equals a plus bx. And so we get all those numbers from the table, right? I like just putting the words into the equation. So this is going to be price, or the predicted price, right? Put a little hat on it. It's the predicted price is equal to, all right, our A, our y-intercept, is the constant right here. 38,257. And our slope, all right, that is the miles driven. That's the variable. The slope is right here. Negative 0.16292 times, and again, you could put x if you wanted to, but I like putting the variables right into the equation, times the miles. So there is our regression equation. We are testing, hey, is this an actual slope? Is this an actual relationship, or is this number just from sample variability? Was it just random chance that we happen to see a downward trend here? Or is there actually something happening? And so we have to test that. And so what's going to essentially end up happening is we are going to put that value on a t-distribution. Let's see, 0 is right here. That value is going to become a boundary. And we're going to see, hey, it's a negative value. What are the chances of getting a value like that, or smaller, in this case? What are the chances of getting a value like that, or smaller, by random chance alone? But we can't use that value as the boundary. We have to standardize it. So we're going to standardize that value into our standardized t statistic. All right, that's going to go over here. And then we will do our TCDF, our cumulative function, to find this probability. So first, to our T statistic, remember it's always your statistic minus your parameter divided by the standard deviation. It's a z-score essentially, right? We're finding the z-score. How many standard deviations away is this slope that we got? So in this context, our statistic is a slope. The parameter is what we assume to be true. We assume the null is true, right? Our sampling distribution is always based off the null hypothesis. We assume the null is true. And the standard deviation, we estimate that with the standard error of the slope. It's the standard error of the slope. I'm hoping that formula does look like a z-score to you. It is basically just a z-score. So the slope is negative 0.16292, which those of you who watched the video, did you see my screw up in the video? I messed up in the confidence interval there. I forgot the negative when I did this problem for the confidence interval. I forgot the negative. Oops, happens to the best of us. Let's see, our null hypothesis. What's our null? Right here. The null is that there is no association. The null is that the slope is 0. The standard error, well, right here. The standard error for the slope is right here. 0.03096. And you used that in the previous video. Same idea here. All right, so there we've got everything. I need to do that on a calculator now. Let me pull up a calculator. Can't do that many decimals in my head. Loading. Loading. There we go. Make that a little bit larger. All right, let's type that in. So we get negative 0.16292 minus, I don't need to do minus 0. What am I doing? Minus 0 doesn't change anything. So divided by 0.03096. So negative 5.26 it looks like. So negative 5.26. So remember, that's essentially a z-score. That means our slope is 5.26 standard deviations away from the middle, away from the null. Okay? It's 5.26 standard deviations away. That is my boundary right here. Okay? So, how weird is that? How likely is it that we could have gotten a slope that's 5.26 standard deviations away? Well, that is simply a TCDF. I got to find this area, right? To find the area, it's a CDF function. So it's a TCDF. I'm going to plug that into the calculator, and it's going to give me the probability. So let's see. I'll do it on the Casio first, then I'll pull up the 83. Or the 84, sorry. So I need to go to distribution, TCDF. My lower value, let's see, I want the area to the left. So that's going to be a really big negative number. My upper value, well, that's my boundary, negative 5.26. My degrees of freedom, Oh, we got to do that still, don't we? All right, what are my degrees of freedom? Remember, degrees of freedom for a t-distribution. In this case, it's n minus 2. All right, it's n minus 2 because we have two variables, x and y. So it's n minus 2 this time. What was our sample size? 1, 2, 3, 4, 5, 6, 7, 8 on the top, and then 9, 10, 11, 12, 13, 14, 15, 16 trucks. So our sample size was 16 minus 2. So our degrees of freedom were 14. Degrees of freedom, 14. All right, go through, execute, calculate that, and we get a p-value of 6 point something. Oh, but times 10 to the negative 5, right? So to the negative 5, that'd be 4 zeros. 1, 2, 3, 4, and then a 6. There is our p-value. I guess for my TCDF, my lower was like negative 1,000 or 10,000. My upper was negative 5.26, and my degrees of freedom was 14. And there is my p-value right there. There was a 0.0006 probability of getting a slope like this one or smaller by random chance alone, which that's so low that never happened, so we definitely reject the null. All right, there is a negative relationship here. We do definitely have evidence of a negative relationship, a negative slope. Whew. All right. I'll write the conclusion sentence here in a second, but that's not new. This is the new stuff. Take a look at that screen. Talk to me. Questions, concerns, comments, angry emails. Anything there not make sense? All right, good questions. Yeah, is the null always going to be 0, and why is the null 0? So the null, no, I don't think the null will always. I have seen some questions where the null isn't 0. Okay, it can happen. I think oftentimes it is 0 because the null is oftentimes there is no association, okay? If the null is that there is no association, then the slope is 0, okay? Then the slope, I have seen some problems on the online stuff while it was kind of working for me, where they made some problems where the null was 1. Like if you think two things are the same, then if they're the same, that gives you a y equals x line. If that's your null, then the slope would be 1. I did see a few scenarios where they made work that way. Most of the time it is 0 because your null is that there is no association between the two. And if it's no association, that means your slope is 0, and so your null slope will be 0. Hopefully that kind of makes sense, yeah. But a scatter plot that is just random, a scatter plot that's random that has no relationship, when you do the linear regression, it'll just be a line, a horizontal line right through the middle, and that has a slope of 0. Most of the questions, the null is that there is no association that I've seen. But that's not 100%. Good questions, good questions. Anything else? Anything else that didn't quite make sense? When it boils down to it, this is 2 steps. It is just 2 steps. Step 1, find the z-score. Okay, that's step 1. Find the z-score. Step 2, find the probability of getting that z-score. I'm hoping you can see it is basically just 2 steps there. Find the z-score and use the z-score to find a probability. Everything else was kind of just background information to make sure you kind of understand what the heck it is we're doing and why, but it is basically 2 steps. All right, let's do 11, 10. Let's do one more real quick. I'll do another one in like 5-6 minutes. Time me, all right? Time me. So I can hopefully prove to you it's not that bad, it's not that long. And I think seeing it without all the explanation does sometimes help see the big picture, all right? So I'll do this one more time without as much explanation, just so you can see the process. Maybe that will give you some more questions to ask. Oh, the conclusion. Oops, my bad. So because our p-value is less than, I think alpha was 0.01. Yeah, alpha of 0.01. We reject the null hypothesis. We have convincing evidence of a negative linear relationship between the price of a Ford F-150 and the miles it has been driven. There we go. I'm hoping that sentence, nothing new there, right? Most of that should be pretty straightforward. We've written that before. All right. Now it's time for the quick question. All right, 11, 12. Time me. Many people believe that students learn better if they sit closer to the front of the classroom. Does sitting closer cause higher achievement, or do better students simply choose to sit in the front? To investigate, a statistics teacher randomly assigned students to seat locations in the classroom for a particular chapter. I feel like I should do that someday. And recorded the test score for each student at the end of the chapter. Here are the data, along with output from a regression analysis. So instead of doing a confidence interval on this time, we're going to do a test. We're going to ask, is there actually convincing evidence of a negative linear relationship? So the farther you sit, the lower your test score is, okay? Between row number a student sits in and their test score at the end of the chapter. So our null hypothesis here is that there's no relationship. It doesn't matter where you sit. It's all random kind of thing. All right, no relationship. So this one will be a slope of 0. Our null is that there's no relationship between your grade and where you sit. Our alternative is that there is a relationship, that slope is less than 0. Where b is the true slope of the regression line relating row number and grade, test grade, right? Test grade. Ooh, I'm going to add this in there for students like these. It's an experiment, right? We didn't randomly sample our participants. They weren't exactly volunteers, I guess, either, but they are not a random sample, so I do need to put 4 students like these. Plan. All right, let's assume the conditions for inference have been met here, okay? So let's keep going on to the do. We are doing a t-test for slope. So the first thing is to find your z-score, the t-statistic for our t-distribution. So that is the slope, which is, oh, let me write the equation. That's not a bad idea. So we're doing our grade is equal to, there's the y-intercept, minus, here is the slope. All right, it's negative, so that's why it's minus. And then row number, right, is our x row number. So let's test that slope. So it's negative 1.117 minus, our null is 0, divided by the standard error of the slope, which is that one, 0.947. Put that into my calculator here. Negative 1.117 minus 0, that doesn't do anything, so just divide it by 0.947. Negative 1.179. So that's like a z-score, right? That's like a z-score. So in my t-distribution, all right, that's over here, negative 1.179. What is the probability of getting a number that small or smaller? Well, we do our TCDF, where the lower is a really big negative number. Our upper is negative 1.179. Oh, what are my degrees of freedom? I always forget that. How many data points did we have? 1, 2, 3, 4, 5, 6, 7, 8. So 8, 16, 24, 25, 26, 27, 28, 29, 30. 30. So my degrees of freedom are 30 minus 2, so 28. My degrees of freedom are 28. Menu, stats, distribution, t-distribution, tcdf, negative 1.179, degrees of freedom, 28, and we get our p-value of 0.124. That's kind of big, isn't it? I didn't have an alpha on this one, did I? But no matter what my alpha was, even if it or 0.01, 0.05, or even 0.10, no matter which alpha we had those are the popular ones, 12.5% is bigger than that, isn't it? So we would, no matter which one it was, we would reject the null. Is larger than even an alpha of 0.10, we fail to reject the null. We do not have convincing evidence of a negative linear relationship between test grade and the row a student sits in. Oh, time. What was that? I was at 12, right? 7 minutes? 6, 7 minutes? Not too bad. Not too bad. Crack. Not too bad. All right. You saw it there, nice and quick, start to finish. How do you feel? Questions there for me? Anything there? 6 minutes, 47 seconds. Nice. I think you get like 15 minutes usually on a free response question. I think it averages out to 15 minutes. Possibly like 25 minutes on number 6. Number 6 is always more difficult on the AP test. Number 6 goes above and beyond. So I don't know, like it's going to be something we haven't completely covered because we don't know what it is. Nobody ever knows what's going to be on number 6. They always ask a above and beyond question on number 6. But we'll talk more about that later. What about this? What about this? Anything there surprise you as I was going through? Like, Bolt, wait, why the heck did you do that? All right, cool. Hopefully that does kind of make some sense there. And that's it, ladies and gentlemen. That's it. We're done. No more new content.